Today we're going to talk about section 3.4, chemical bonding in elements and compounds. There are three types of chemical bonds. There are ionic chemical bonds, which is a strong bond, where the electrons are going to be transferred from one element to another. There are covalent bonds, which are strong bonds, where the electrons are shared between the elements. And then there's metallic bonding, which is also a strong bond. The atoms are held together through a sea of electrons. And we will discuss each one of these further in these notes. Let's start with ionic versus covalent. How can we easily identify if a compound forms an ionic bond or a covalent bond? The really simple trick to this is that an ionic bond will always be between a metal and a nonmetal. A covalent bond will always be between a nonmetal and a nonmetal. So simply by looking at the formula or the name, if a metal is present, it will have ionic bonds. And we'll talk about subatomically what that means in a second, but let's just see if we can identify ionic versus covalent compounds by looking at the names and formulas. So here we have Ca2O. The second element, by the way, is always going to be a nonmetal. So to determine whether you have a metal, you really just need to look at the first element. If the first element is a metal, then it will be an ionic compound. So here, calcium is a metal, MgCl2, magnesium is a metal, chlorine is a nonmetal, HCl, 2 nonmetals, H2O, 2 nonmetals, potassium iodide, metal and nonmetal, N2O5, 2 nonmetals, carbon dioxide, 2 nonmetals, lead chloride, metal nonmetal. Notice again, all the second elements are nonmetals, so you really are only looking at the first element to determine whether you have a metal in your compound or not. So if you have 2 nonmetals, you are going to have covalent bonds. So H2O is going to have covalent bonding in it. MgCl2 is going to have ionic bonds. Ca2O will have ionic bonds. CO2 will have covalent bonds. N2O5, 2 nonmetals, covalent. PbCl2 has a metal, so it will be ionic. Potassium iodide, ionic, and HCl, covalent. Let's take a look at these and see if you can determine whether they should go under ionic or covalent. Silicon dioxide. Silicon is considered to be a nonmetal, so it's going to be covalent. MgOH. This is what we call a polyatomic. We'll get into that later. You're looking at the magnesium. It's a metal, so it will have ionic bonds. AgNO3. Ionic bonds. H3O. Covalent. C12H22O11. Covalent. NiO. Ionic. Au3N2. Ionic. H2SO4. Covalent. And that's that. Notice that all the ionic bonds have metals. All the covalent bonds have nonmetals. Let's take a look at ionic bonds closer. What is an ionic bond? What makes it different from a covalent bond besides the fact that it has a metal? To do this, we need to look at atomic stability. The electric forces between oppositely charged electrons and protons holds the atoms and molecules together, and thus are the forces that cause compounds to form. Atoms of noble gases are unusually stable. Compounds of these atoms rarely form because they are almost always less stable than the original atoms. The unique noble gases To understand the stability of noble gases, it's helpful to look at their electron dot diagrams. So here in the electron dot diagram, it shows the valence electrons, or the electrons in the outermost ring that are responsible for chemical bonding. With the exception of helium, notice that all of the noble gases have 8 valence electrons in their outer shell. Electron dot diagrams show only the electrons in the outer energy level of the atom. The noble gases are stable because they each have a complete outer energy level of 8. Helium is the exception with 2, but in the first ring, a full first ring has 8 electrons in it. I'm sorry, has 2 electrons. Notice that 8 dots surround krypton, neon, xenon, argon, and radon, and 2 dots surround helium. If you look at hydrogen's dot diagram, hydrogen contains 1 electron in its lone energy level. A dot diagram for hydrogen has a single dot next to its symbol. This means that hydrogen's outer energy level is not full. It is more stable when it is part of a compound. In contrast, helium's outer energy level contains 2 electrons. Helium already has a full outer energy level by itself and is chemically stable. Helium rarely forms compounds, but by itself, the element is commonly used as a gas, or is a commonly used gas. When you look at the elements in groups 13 through 17 or 3 through 7, you see that each of the elements fall short of having a stable energy level. All the elements in group 1 have 1 valence electron. All the elements in group 2 have 2, 3, 4, 5, 6, and 7. The elements are trying to get 8 valence electrons in their outer shell, with hydrogen and helium being the 2 exceptions, which only need 2 valence electrons in their first ring. Each group contains too few electrons for a stable level of 8 electrons. How does hydrogen or any other element trying to become stable gain or lose its outer electrons to become 8? They do this by combining with other atoms that also have partially complete outer energy levels. As a result, each achieves chemical stability. This illustration shows electron dot diagrams for sodium and chlorine. Sodium is in group 1. It has 1 valence electron in its outer ring. Chlorine is in group 7. It has 7 valence electrons in its outer ring. When they combine, sodium will lose its 1 electron and chlorine will gain that electron. When sodium loses that 1 electron, notice that its new inside shell has 2, 4, 6, 8. So it has achieved its stability by losing its 1 valence electron. Chlorine picks up that electron, and now it has its 2, 4, 6, 8 in its shell, thus achieving stability for chlorine. You can see from the electron dot diagram that chlorine now has a stable outer energy level. Sodium had only 1 electron in its outer energy level, which it lost to combine with chlorine in sodium chloride. Look back to the next outermost energy level of sodium. This is the new outer energy level, and it is stable with its 8 electrons now. Stability is reached. When atoms gain, lose, or share electrons, an attraction forms between the atoms, pulling them together to form a compound. This attraction is called a chemical bond. A chemical bond is the force that holds atoms together in a compound. Elements react with other elements to form compounds. All elements want 8 valence electrons, with the exception of hydrogen and helium. So 8 is the magic number of valence electrons that all the elements on the periodic table are trying to achieve. Atoms can gain or lose electrons to become stable with 8 valence electrons. As we saw with sodium and chlorine, let's take a look at their Bohr diagrams. Sodium, which has 3 rings, has 1 valence electron in its outer ring. Chlorine which has 3 rings as well, has 7 electrons in its outer energy level. So, in order for both of them to achieve 8 valence electrons in their outer energy level, one of 2 things can happen. Option 1 is that 1 electron from sodium will be picked up by chlorine, thus eliminating its sodium's 3rd shell, and its new outer ring has 8 shells. Chlorine, after picking up that electron, has 8 electrons in its outer shell as well. Option 2 is the 7 electrons from chlorine could possibly be picked up by sodium, thus sodium achieving 8 electrons in its outer energy ring, and chlorine achieving 8 electrons in its outer energy level. Which option do you think is more likely? The option of the 1 electron from sodium going over here, or the 7 electrons from chlorine going over to the sodium? The correct answer is option 1. The reason that is option 1 is that it takes less energy to pull 1 electron away from sodium than it does to pull 7 electrons towards sodium. So option 1 is the correct occurrence. Let's take a look at group 2 and group 6 compounds. Magnesium, which has a configuration of 2, 8, and 2, and sulfur, which has a configuration of 2, 8, and 6. In order for magnesium and sulfur to both achieve 8 electrons in their valence shell, one of 2 things can happen. The 2 electrons from magnesium can be pulled over to sulfur, thus eliminating the 3rd ring, and magnesium having 8 in its new outer shell, and sulfur also now having 8 in its outer shell. Option 2 would be for the 6 electrons in sulfur's outer ring to come over to magnesium. Thus, magnesium getting 8 here and sulfur getting 8 over here. Which option is more likely? The correct answer is option 1. It is easier to pull 2 electrons towards sulfur, requiring less energy, than it is to pull 6 electrons from sulfur the other way. Let's take a look at group 3. Aluminum, which has a configuration of 2, 8, and 3, and phosphorus, which has a configuration of 2, 8, and 5. Option 1 would be for the 3 electrons of aluminum to be pulled over to phosphorus, thus aluminum achieving 8 valence electrons and phosphorus achieving 8 valence electrons. Option 2 would be for aluminum to pull those 5 electrons from phosphorus over to it. Which option is more likely to happen? Again, option 1. It is easier to pull 3 electrons towards phosphorus than it would be to pull 5 electrons towards aluminum. It takes less energy. So, option 1 again is the correct answer. If you are in group 4 with 4 valence electrons, let's say carbon for example, group 4 can gain or lose 4 electrons with each other. So the periodic table creates this nice little pattern. If you are in group 1 with 1 valence electron, you are always going to lose that 1 electron to someone else on the right-hand side of the table. Group 2, you will also lose your 2 valence electrons. Group 3, you will lose your 3. So in other words, group 1, group 2, and group 3 are going to lose their valence electrons. Group 4 can go either way. When you get to group 5, 6, and 7, because it's not easy to lose 5, 6, or 7 valence electrons, they are going to gain either 3 electrons, 2 electrons, or 1 electron. Whatever number brings them up to 8. So they're going to gain 3, 2, or 1 over here. So let's take a look at these examples. Lithium. Let me go back to this one for just a second. The general rule is that metals lose their electrons, nonmetals gain electrons. So lithium, which is a metal, which is in group 1, has 1 valence electron. It will lose its 1 valence electron. Nitrogen, which is a nonmetal, which is in group 5, is it going to gain or lose electrons? Nonmetals gain electrons. How many will it gain to get to 8 electrons? 3. So notice it doesn't gain 5, it gains enough to bring that total up to 8. Magnesium is a metal. It has 2 valence electrons. It will lose those 2. Fluorine is a nonmetal. It is in group 7, so it has 7 valence electrons. It will gain 1 to bring it up to 8. Notice that the nonmetals gain enough electrons to bring them up to the number 8. Sulfur is a nonmetal. It has 6 valence electrons because it is in group 6. It will gain 2. Aluminum is a metal. In group 3, it will lose its 3 valence electrons. Francium is a metal. In group 1, it will lose 1 valence electron. Now, let's take a look at what happens when sodium and chlorine transfer electrons as far as the charges go. This is a picture of the sodium Bohr model with all of its protons and electrons, and this is a picture of the chlorine atom with its 17 protons, 17 electrons. So initially, sodium has 11 protons, 11 electrons. The 11 positives cancel with the 11 negatives, and the total charge is 0. Chlorine, which has 17 protons and 17 electrons, cancel each other out to give a total charge of 0. Now, when sodium and chlorine combine to create a compound, NaCl, we have seen that that 1 valence electron will be transferred to chlorine. So sodium gets its stable 8 here, chlorine gets its stable 8 here. What happens to the charges, though, is something different. This electron gets pulled over to chlorine. How many protons does sodium now have? That has not changed, that is 11. But now it only has 10 electrons. So we say that its overall charge is positive by 1 charge. It has 1 extra proton than electron, and so now it becomes what we call a charged particle. For the chlorine's proton stays 17, but now it's picked up an electron, so now it becomes 18. So now we say chlorine has a charge of -1 because it has an extra electron. An ion is a charged particle because it has either more or fewer electrons than protons. The metals are going to become positive ions because they are always going to lose their electron. Nonmetals are always going to become negative ions because they always gain an electron. The oxidation number is the positive or negative number that indicates how many electrons an atom gained, lost, or shared to become stable. In other words, it is the charge on that atom or that ion now that it's charged. We call the name of this ion Na with a superscript of +1 written in the corner. The +1 indicates that sodium now has a charge. When the charge is 1, you don't have to write the 1. It is understood to be 1 if that positive sign is there. If your charge is something other than 1, you do need to indicate that by putting 2, 3, or possibly 4. For chlorine, we write the name of this ion as Cl-. The minus tells us that now chlorine has a charge of -1. So sodium is a metal. It has 1 valence electron. It loses 1 to become Na positive, and the name of it would be sodium. Chlorine is a nonmetal that has 7 valence electrons. It gains 1 electron to become Cl-, and when a nonmetal becomes an ion, the suffix of its name changes to the letters IDE. So notice that these two things are a little different. When the nonmetals become ions, their suffixes change to IDE. Let's take a look at beryllium and oxygen. So beryllium initially has 4 protons and 4 electrons. Its total charge is 0. Oxygen has 8 protons, 8 electrons. Its charge is 0. Beryllium is going to lose its 2 electrons to oxygen. So now it has a charge, now it has 2 electrons and 4 protons. We say that it has a charge of 2 positive. Oxygen now has 2 extra electrons, so its number of electrons is 10. Its charge is now negative 2. You can put the negative sign in front of the 2 or behind the 2. It does not matter. We call this ion for beryllium Be2 positive, which comes from its charge, and we call the oxygen ion O2 minus to indicate that now it has 2 extra electrons. So beryllium is a metal. It has 2 valence electrons. It loses 2 electrons to become Be positive 2. The metal name does not change. It stays beryllium. Oxygen is a nonmetal. It has 6 valence electrons. It gains 2 electrons to become O2 minus. The suffix for the oxygen ion becomes oxide. So notice that the suffixes change for the nonmetal ions. Let's take a look at boron and nitrogen. Boron has 5 protons and 5 electrons to begin with. Nitrogen has 7 protons and 7 electrons to begin with. The 3 electrons from boron, the 3 electrons from boron are going to be pulled over by the nitrogen. And so now the boron has 2 electrons and 5 protons. The nitrogen has 7 protons and 10 electrons. Boron now has a 3 positive charge. Nitrogen now has a 3 minus charge. We call this B3 positive ion, and we call this N3 minus ion. So boron, which is a metal, has 3 valence electrons. It loses 3 electrons to become B positive 3, and its name is boron. Nitrogen is a nonmetal with 5 valence electrons. It gains 3 electrons to become N3 minus, and its suffix changes to IDE. All right, let's take a look at this table. You may press pause on the video to see if you can fill this table in on your own. All right, aluminum is a metal with 3 valence electrons. It is going to lose 3 electrons to become Al positive 3, and the name of it is still aluminum. Tellurium. Tellurium is a non-metal. It has 6 valence electrons. It is going to gain 2 to become Te2 minus. Notice that when you gain electrons, the nonmetals, their charge becomes negative. So the name of this is going to change to telluride. Potassium is a metal with 1 valence electron. It's going to lose 1 electron to become K positive 1, and its name stays potassium. Gold is Au. Gold is not a normal metal. It is a transition metal. So because it's not in a normal A group on the periodic table, its number of valence electrons has to be given to you in the problem. So here it tells us that gold has 2 valence electrons. Because it's a metal though, it's going to lose those 2. All metals are going to lose their electrons. Its formula becomes Au2 positive, and its name is going to be gold parentheses 2. For the transition metals, you have to put the oxidation number of the transition metal in Roman numeral next to the name. Silver is Ag. It is a transition metal. It tells us that its oxidation number is 1. It is going to lose 1 electron to become Ag1 positive, and its name is going to be silver 1, and that's it. Phosphorus is P. Wow. Messed up there. My bad. sorry, we're not writing the symbols. We are writing, this is a metal, this is a metal, phosphorus is a nonmetal. Number of valence electrons of phosphorus is going to be 5. So it's going to gain 3 to become P3 minus, and its name becomes phosphide. Iodine is a nonmetal. Its number of valence electrons is 7. It's going to gain 1 electron to become I minus 1, and its name becomes iodide. So the general rule is that all elements in group 1 will lose their valence electron to take on an oxidation number positive 1. All elements in group 2 will always lose their 2 electrons to become positive 2 charges. Elements in group 3 will become positive 3. Group 4 can go either way, so it's positive or minus 4. Group 5 is always going to gain 3 electrons to take on a negative 3 oxidation number. Group 6 is always going to gain 2 electrons to become negative 2, and group 7 is always going to gain 1 to become negative 1. So instead of having to go through those pictures and counting electrons, you can now use this cheat sheet to kind of instantaneously tell you what the oxidation number is going to be on each of those elements. Strontium. So strontium's oxidation number is going to be positive 2. Francium. Its oxidation number is going to be positive 1. Polonium. Its oxidation number is going to be negative 2. Bromine. Its oxidation number is going to be negative 1. Aluminum. Its oxidation number is going to be positive 3. Determine the oxidation number of each ion, then write the name of the ion. So calcium, using this cheat sheet, is going to take on a positive 2 charge. Bromine is going to be Br negative 1. Nitrogen is going to be N minus 3. Oxygen is going to be O 2 minus. Rubidium will be Rb plus 1, and magnesium will be Mg plus 2. Phosphorus will be P3 minus, sulfur S2 minus, chlorine Cl minus 1, potassium K plus 1, beryllium Be plus 2, and gallium Ga plus 3. It does not matter if you put the positive or minus sign before the number or after the number. And we will end day 1 here.